everybody. This is the last session of this year's ITCS. And we're going to have 1, 2, 3, 4, 5 papers. Okay, yeah, so the first paper is by Leonard Numesh. I guess, frankly, my reaction to this paper was, wait a minute, this is the innovations in theoretical computer science, not innovations in game theory. Okay, so it's. I'm sure that I looked, and the game theorists have not suspected this, have not seen this twist of their game, and I am positive that. They will regret it, okay, that they are going to kick themselves. Because, they have worked on team theory, they have worked on many things, but they have not seen this very interesting phenomenon. In other words, that if the two players are teams, uncoordinated teams, then a very interesting phenomenon happens, namely that depending on the different degree of coordination, you can lose a lot of utility, okay? And that's even in, this happens even in two strategy zero-sum games, okay? And the gap is essentially as big as it can get, even if you have a team of two players, okay? And then it degrades even more. So this is, I think this is a very surprising new area. It's very surprising phenomenon that we have not noticed. This I repeat that economists have been very interested in the loss of utility due to the lack of coordination among teams. Good. So the second. So incidentally, these are these 5 papers are very much core ITCS papers. The next one is by Xi Yu and Bo. Sorry. And it's basically it is one step in the in understanding the communication of Population equilibrium. So there has been recent work on that, and in fact, in last Fox there was a paper by Aviet which had a similar result. In fact, a little stronger, okay? So, but ITCS is not a conference where we punish people for missing 2 months and a log n factor, okay? And the reason we don't is because this paper, first of all, it has much simpler, very simple proof, very transparent proof, and also it elucidates in a very nice way a subtle difference between two concepts of approximation in equilibrium. Vanilla approximation and well-supported approximation. So then we have a paper by Daniel and Vergi. So it's a very nice paper on weighted matching. Okay, dynamic weighted matching. So very hard, very interesting problem, and they make it is part of a very recent exhilarating trend to use reductions within polynomial problems, to reveal very interesting phenomena. For example, what they show is that you can that weighted matching is essentially not much harder than cardinality matching. Okay, and the other one is that this annoying dependence on the log of W can be reduced to log. Okay, and as we know, log of humanity is 5. Okay, so right. So then you have this paper by Ryan. SOS is not obviously automatizable, even approximately. So, so basically, this is a powerful ring of caution, okay? That we have been, it's sort of, we have been claiming for a long time that, for example, you can find certificates of feasibility for sum of squares, for polynomials of second degree in sort of, that are themselves second degree, and therefore, and then, sorry, degree D, degree order D, and therefore, the problem looked tractable, and we have been claiming that, and so and Ryan points out that we have been sweeping under the rug something that can explode under the rug, okay, and that's the issue of precision, all right, and he gives an example where for second degree polynomial exists, but the coefficients are of exponential precision. Okay? And not only that, but even the approximate version of the problem has a similar. So this, I believe, is going to make a lot of people working on some of the most important and hot areas, trying to revisiting sort of our assumptions and work. Finally, if I may be very frank, this is really my favorite paper in all of ATCS. It talks about my favorite subject, which is problems in NP that always have solutions. And I mean, sometimes it seems more obvious that TFNP is not P than that NP is not P, okay? But and in some sense it is because it has been proven that even if you assume that even on the assumption that P is not equal to P, you cannot prove that TFNP is not equal to P. So, what Pavel, Moni, and Aaron do? They prove the same thing. They prove what we wanted to prove for average case. Okay, so you can go from average case hardness in NP to average case hardness in TFNP. This is sort of this is sort of an epic result, I think. And it's also, I mean, we always suspected that that TFNP has something to do with cryptography. After all, PBP is like hash functions, and factoring is RSA. But we have been sort of, we waited for a long time for the cryptographers to actually seriously work on this. And here you have really interesting use of a lot of things, a lot of sophisticated techniques used, like zero knowledge. So there you have it. Let's start with